and welcome to another fun and easy machine learning tutorial on decision trees. A decision tree is a type of supervised learning algorithm that is mostly used in classification problems. A tree has many analogies in life, and turns out it has influenced a wide area of machine learning, covering both classification and regression trees, otherwise known as CART. Please join our notification brigade by subscribing and clicking that bell icon. So a decision tree is a flowchart-like structure where each internal node denotes a test on an attribute, each branch represents an outcome of a test, and each leaf or terminal node holds a class label. The topmost node in a tree is the root node. In decision analysis, a decision tree can be used to visually and explicitly represent decisions and decision making. As the name goes, it uses a tree-like model of decisions. So the advantages of CART: it is simple to understand, interpret and visualize. Decision trees implicitly perform variable screening or feature selection. It can handle both numerical as well as categorical data. It can also handle multi-output problems. Decision trees require relatively little effort from the user for data preparation. And nonlinear relationships between parameters do not affect the tree performance. The disadvantages of CART, however, is that decision tree learners can create overcomplex trees that do not generalize the data well. This is also known as overfitting. Decision trees can become unstable because small variations in the data might result in a completely different tree being generated. This is called variance, which needs to be lowered by methods of bagging and boosting. Greedy algorithms cannot guarantee to return the globally optimal decision tree. This can be mitigated by training multiple trees, where features and samples are randomly sampled with replacement. Decision tree learners also create bias trees if some classes dominate. It is therefore recommended to balance the dataset prior to fitting with the decision tree. If we look at some applications of a decision tree, we can predict whether a customer will pay his renewal premium with an insurance company. So you can predict yes if you will or no if you won't. You can use it to predict Titanic survival statistics. So if male or female as well as age, what are the chances of survival? You can use it to determine if a person is male or female based on their height and weight. Also, you can use it to determine a price of a home based on how many rooms as well as the floor size. A decision tree is drawn upside down with its root at the top. So in the image, let's look at the primary differences and similarity between classification and regression trees. Regression trees are used when the dependent variable is continuous. Classification trees are used when the dependent variable is categorical. In the case of regression trees, the value obtained by terminal nodes in the training data is the mean or average response of the observation falling in that region. Thus, if an unseen data observation falls in that region, we'll make its prediction with a mean value. In cases of classification tree, the value or class obtained by the terminal node in the training data is the mode of observation falling in that region. Thus, if an unseen data observation falls in that region, we'll make its prediction with a mode value. So the splitting process is continued until a user-defined stopping criteria is reached. For example, we can tell the algorithm to stop once the number of observations per node becomes less than 50. So in both cases, the splitting process results in fully grown trees until the stopping criteria is reached. But the fully grown trees is likely to overfit data, leading to poor accuracy on unseen data, and this brings pruning. Pruning is one of the techniques used to tackle overfitting. We'll learn more about it in future lectures. So how can an algorithm be represented as a tree? For this, let's consider a basic example that uses the Titanic dataset for predicting whether a passenger will survive or not. This model over here uses three features from the dataset, namely sex, age, and number of spouses or children along. We can abbreviate this to SIB-SP. In this case, whether a passenger died or survived is represented as red and green text respectively. Although a real dataset will have a lot more features, and this will just be a branch in a much bigger tree, but you can't ignore the simplicity of the algorithm. So what's actually going on in the background? growing a tree involves deciding on which features to choose and what conditions to use for splitting, along with knowing when to stop. As a tree generally grows arbitrarily, you need to trim it down for it to look beautiful. So let's start with common techniques used for splitting. So how does a tree decide where to split? So the decision for making strategic splits heavily affects a tree's accuracy. The decision criteria is different for classification and regression trees. Decision trees use multiple algorithms to decide to split a node in 2 or more subnodes. The creation of subnodes increases homogeneity of resultant subnodes. In other words, we can group our data in regions based on data that have similar traits. Decision tree splits the nodes on all available variables and then selects the split which results in the most homogeneous subnodes. We'll tackle an example soon in this lecture. The algorithm selection is also based on the type of target variables. So let's look at the 4 most commonly used algorithms in decision tree. 1. Beauty index. 2. Chi-squared. 3. Information gain. 4. Reduction in variance. So we'll not go into detail on these algorithms, as some involve quite a lot of math, and most of the hard work is done within scikit-learn's libraries. Let's gain an intuition of how splitting the data would work if we had to do it manually. So over here we have arbitrarily generated data. We have x1 and x2, which are our independent variables. If we had to look at this data, we can split it into 5 regions. So we can draw a line here at x1 equals 20, as well as x2 equals 50. And then another one over here at x1 equals 25. And then a last split over here between by x2 equals 30. So we have regions R1, R2, R3, R4 and R5. And we do this empirically. The algorithms I mentioned earlier will do this for you. Now remember, you can split it a bit further into more regions. So say for example, we can split R4 over here and that will result in more subnodes in our tree. But for now, let's just have 5 regions. So we start off over here at our root node. So we ask ourselves, is x1 less than 20? So we go either yes or no. So if yes, is x2 less than 50? So if you look at our graph over there, and then we separate that into R1. So if yes, we have R1, if no, we have R2. Then we go to our other branch and we ask, is x1 less than 25? So over here we look at if it's less than 25. If yes, then it's R3. If no, then we ask ourselves, is x2 less than 30? And if yes, we got R5, and if no, we got R4. So as you can see, that is really simple. So this is all the basics to get you on par with decision tree learning. Decision trees are also very useful when used with other advanced machine learning algorithms like random forests and boosting, which we shall cover in future lectures. A popular library for implementing the algorithm, scikit-learn. It has a wonderful API that can get your model up and running in just a few lines of code in Python. So thank you for watching. Please don't forget to smash the like button and click that bell icon to become a part of our notification brigade. And also support us on Patreon. See you in the next lecture.